Hello everyone, welcome again to CodeTab. In this series of videos that we are solving the most exciting, the most interesting problems that we find on the internet. And today we are solving problem number 15 from Project Euler.net, which is called Lattice Paths. Let's just read the description about this problem. Starting in the top left corner of a 2x2 grid, and only being able to move to the right and down, there are exactly 6 routes to the bottom right corner. Okay, so we have the grid 2x2, and starting from this point here all the way to the point down below in the grid, we have exactly 6 routes. Yes, we can just go right and down, so we can just go this way, or making a curve in the middle, or just going straight through the middle, or then going bottom. There are 6 ways to do that. So the problem asks us how many such routes are there through a 20x20 grid. Yeah, so this is a very interesting problem because a normal brute force solution to solve this problem is not gonna cut, because the number of possibilities grows significantly as the grid grows in size. So we're gonna have to have a more clever solution to solve this problem. Well, let's start then with the brute force solution, then we go for a more clever solution, shall we? So I will create a new Python package here, problem 15, yes, add to my GitHub, and then my problem 15, okay? My solution then will be quite simple, my initial solution, right? I am gonna implement a recursive solution to this problem. We can model this lattice path as a grid, as a two coordinate grid, right? We're gonna have 2 coordinates in this grid, x and y. X is gonna represent the horizontal or the moving right, and y is moving down. So we can imagine that our initial position is 0, 0, and by increasing one position to the right, we increase x to +1, right? And moving a position downwards is increasing y +1, right? In this way, we can basically explore all the possibilities by always increasing one position in each case that we increment, right? We would stop something like this, such a implementation, when we reach the bottom, right? So this is a kind of like a simple implementation, and we can implement this through a recursive means, right? In a recursive implementation of this, we're just gonna call the same function over and over again by increasing either x or y. Let's give it a try for this implementation, and then we see if there are better ways to implement it, right? So let's go. In this case here, I'm gonna create a function called lattice path, right? And it's gonna receive 2 coordinates, x, which is an integer, and y, which is an integer as well, and it returns another integer, which is the response, right? So let's put here our common commentaries on this. So recursively calculates the lattice, what do you call here, lattice routes, the number of lattice routes, right? And it receives x coordinate and y coordinate, and it should return the number of routes. Since it's a recursive solution, we always need to think this recursivity will stop, and it will always stop when we reach our final number, right? In this case, it's 20. It could be 2 as well, which is the example, right? So if x is equal to 2, which is our final destination, and y is equal to 2 as well, we return 1. Right, so it's just like we reach the bottom, and then every return we're gonna just increase 1 increment in the number of results that we have, right? In this case, we're just gonna have a variable here called result, which will accumulate the result, right? And if our x is smaller than 2, right? So let's check first the horizontal path, right? We're just gonna increment all the solutions, that is, calling the same function for the right route, right? So for the horizontal route. So we're gonna just call the same function over again, and we increment x. And y is gonna be the same. And we do the same thing for y, right? So y is minus equal to 2. We just do the same thing for y. So, but instead here we increment y. That should do the trick. In the end, we just return result. Let me just organize this better. This should give us the result for 2. Let's give it a try. Lattice path, we just pass it 0, 0, right? Python problem 15, problem 15. Oops, I didn't put print. Let's put a print here and then we do it again. Yes, 6. 6 is our result. But I will guess here with you that this is not going to work for 20, right? So let's just replace here, which is 20, our final the result to the problem. And executing it, it's going to take a very long time to process this and give me the result. As I said, it is the number of recursive calling here when the grid is 20 by 20 is too large. We're going to have a better solution to this problem if we wanted to solve it. Right. One potential solution for this particular problem is using dynamic programming. I think it's worth to explain a bit what is dynamic programming. So I prepared a little explanation about it. So dynamic programming is a technique that enables us to solve complex problems by breaking them down into smaller problems. Then we solve these smaller problems, store their results, or somehow combine their results to solve their main problem. It's not every algorithm, it's not every computational problem that you can apply dynamic programming. And in my view, there are two situations that of problems that you can solve through dynamic programming. The first of these characteristics is called optimal substructure. So this characteristics states that like the solution to the main problem must come from combining solutions of smaller problems. So it's the characteristics of breaking a bigger problem into a smaller one. One example is the Fibonacci series, in which the solution of the Fibonacci series for a certain n number is given by the two previous numbers of the Fibonacci sequence, n minus 1 and n minus 2. So, and another characteristic is whether you have overlapping subproblems. So overlapping subproblems is the case that like you have smaller problems and they occur very often. We saw this in a previous problem that we tried to solve, problem number 14, the collapse sequence. That there were a lot of repeated computation that we can store instead of just computing them all the time. And once we stored, we don't have to compute them over and over again. That saves us time, although there is some costs with memory, but memory is very cheap, so we can just store it. Dynamic programming solutions have two main techniques. You have like top-down and bottom-up. In the top-down approach, it's basically called memoization. You try to break the problem down, check if the subproblem has already been solved. If not, you compute it. If yes, you just use the computation that you already stored. And then combine the solutions as you move up again. So this is basically what we did for the collapse sequence in problem number 14. An alternative dynamic programming solution is going bottom up. Instead of breaking problems down, we start from smaller problems and we work our way up, combining the subproblems to solve the main problem. In this case, it doesn't require us to check if computations has already been performed. We just start from the smaller problems and go combining these solutions until we reach our final solution. The lattice path then is a solution that can be solved via the bottom-up approach. We can represent an n versus n grid through an n plus 1 versus n plus 1 matrix. So in this case, it's not like that we're trying to represent the grid itself, but the nodes in the grid. So there is always n plus 1 nodes for each dimension on the horizontal and vertical dimension, right? So a 2 by 2 gives us a 3 by 3 on each of these nodes here on this grid, right? So in this case, the first row and the first columns of the matrix is always initialized with 1, right? Because there is just one solution for horizontally and vertically. So for example, starting from here, and if we just want to reach the rightmost side approach without moving down, there is just one path. Similarly, vertically, if you want to start from the top, going only down, there is just one path. So all the routes horizontally start with 1. The rest of the matrix is initialized with 0. So it looks like this. So the solution for the remaining nodes, for example, to an arbitrary x, y coordinate is always given by the sum of the solution in the same column but the previous row, and the same thing in the same row but the previous column. The solution for a given cell is just summing the cell on the top and the cell on the left, and then you get your result for that sub-problem. For reaching the solution to the main problem, we just need to do the same thing up to the last square here. And then once we go through this matrix, the result to our problem shall be in the last cell of this matrix. So in this case here, a 2 by 2 matrix would give us 6. So 1 plus 1 gives us 2, and then 1 plus 2 gives us 3, 2 plus 1 gives us 3, and then 3 plus 3 gives us 6. The solution is 6. So we can make such implementation to our problem. So let's just create here a function called lattice path dynamic DP, dynamic programming, right? In this case here, I will use an n as input, which will be like our size of our matrix, and it shall return only a int, which shall be the result, right? So in this case, this is dynamic programming to the lattice path solution, right? So this is the size of the grid, right? Okay, and it shall return the number of routes. So the first thing we need to do here is to initialize our matrix, right? Our matrix will be initialized as a vector at first, right? So for each number in the n plus 1 range, and each row shall also be initialized with zeros, right? And I will just initialize a 0, again, n plus 1 times. This gives us a matrix n plus 1 times n plus 1 size. So now we also need to initialize the borders and then sum the rest, right? So we can do this via iterating this matrix. So for I in range n plus 1, and also for j in range n plus 1. So we are iterating here the rows and the columns of this matrix. The first case is in the borders of this matrix. So if I equal to 0 or j is equal to 0, then our matrix in the position I and j receive 1. This is the case that we have here. So it's just like the borders. Otherwise, our matrix in the position I, in the position j, will receive the same row, but the previous column, plus the matrix in the previous row, but the same column. And this should do the trick, right? Once we pass through this matrix, we should return the matrix in the position n. That shall have the final result. Just one thing here for code conventions, I'll do this and this. And instead of calling this one that takes God knows how long, I'm just going to call the lattice path DP, right, the dynamic programming. First, let's test if it works for n is equal to 2. So let's pass n is equal to 2. Okay, so Python, problem 15, let's run it. Yes, it gives us the result, which is 6. If we run this, 6 is the correct result. If we run this for n is equal to 20, it should also give us the result for 20. Let's give it a try. And it gives us a big number here. I hope this number is right. Let's give it a try. And yes, congratulations. The result is correct. So this solution then, it's a way simpler solution than the previous one. If we were to calculate this via checking every path, this has a lot of repeated computations in which we do not need that. So this is just wasteful of computations, right? So the lattice path solution via checking recursively is not the right one. Via dynamic programming, we can just solve it on a squared solution, right? So n squared solution. Since our matrix is just 20, this just gives us 400 computations. For a normal computer, this is nothing. So this is why the solution is given in a very short amount of time. I hope you liked the explanation about dynamic programming. I think it's a very elegant solution to algorithm problems. I hope to see you on the next video. If you liked, please like, share, subscribe, sign on the notification bell to join the videos when they are published. And thank you very much. I see you on the next time.